Okay, welcome back to the last session of the robotics class here in San Antonio. Let me go to my station here, and I want to first go to the textbook and describe to you the table of content of the course, of the book. So you need to know the meaning and the definition of very elementary things at the beginning of the semester. You need to know at least one or maybe more than one definition of a robot. What is a robot? It's that simple, okay? You need to understand the meaning behind coordinate system, joint coordinate system, X, Y, Z, from base all the way to your end effector, your hand. And what is Denevan-Hartingberg transformations? What are those four parameters meaning? Okay, and how do you transform from one coordinate to another coordinate in the process of having two translational and two rotational movements? Remember that? There are four parameters of DH or Denevan-Hartingberg parameters. Two of them were angles and two of them were distances. Okay. Need to know the meaning of kinematics, forward kinematics, and inverse kinematics. Okay. It is much more challenging, as you know, to deal with inverse kinematics than forward kinematics. Okay. One has a straightforward response with answer right away. You just change 6 angles and you see where you end up. That's forward kinematics. And the other one is very difficult because you are given where you want to be. You have to find 6, in the case of 6 degree of freedom robot, you need to find 6 different angles to collectively, one after another, move, change it to be in that one. You're not always guaranteed to get there. Because if you remember from the upper part of 3 by 4 upper part of the transformation matrix, there are 3 times 4, 12 nonlinear algebraic equations, full of sinus and cosinus, sine and cosine. And those are highly nonlinear, and you're trying to find 6 unknowns in 12 equations. Good luck. You see, that's the toughest part of inverse kinematics. So, on an exam situation, I cannot ask you more than maybe 2-link robot, maybe even 1-link robot, 2-link robot. 1-link robot was your first homework, remember? The inverted pendulum. So, go over all your homeworks carefully and redo the homeworks, because you never know, I may pick questions from the homework. And if you have not learned it properly, if you look over the shoulder of somebody else in your group, good luck. Okay? At least this is your last chance to learn something about the basic concepts. Okay? So, in the area of manipulator, you also need to understand trajectory planning. What kind of trajectories do we have? We have trajectory planning in the joint space and trajectory planning in the Cartesian space. For example, there is a device in many manufacturing factories called numerical control machine, NC machine. You may have heard of it. NC machine has a blade which you run it through a piece of metal like copper or whatever, and you give it a shape as a reference input to the control system, NC system. And the blade will move exactly like you were giving it a shape to do. And that's how in the old days you would actually prototype something before 3D printer was around. Okay, you could do prototyping like that. Okay, and if you go to the departments, for example, mechanical engineering departments of workshop where you have technicians are working, a lot of student projects need prototyping. Senior design projects needs prototyping, and that's the kind of things that they need to do. But the reason I brought that up because that NC machine works in the Cartesian space. It's actually working in the real world. So you need to program NC machine that the blade moving the right location, the right trajectory. Okay. You also need to learn the meaning behind Jacobian matrix. It has two different meanings. One is the coefficients of a Taylor series expansion of a nonlinear equation, whether it's algebraic, it doesn't matter, or it's a differential equation, you can linearize them. And it gives you a bunch of Jacobian matrices which are going to be known to you because you're always linearizing with respect to a nominal trajectory. Okay? And that nominal trajectory is known. You plug in the x and u or x and y or what have you, variable, into those matrices and they become known. What is left is going to be a linear portion of it, and you throw away second, third, and fourth order model terms. Okay? Then you pick up a zero term and a first term. That's a linear model. Now the reason you do that, as you all know, you have all taken control classes before, almost the entire classical control system is based on linear system. Okay? A lot of time, linear time invariant system, where you can even use Laplace transform. Or if you take discrete version, like the course I'm teaching in the fall, use Z transform. Okay? You do that. You do your design based on a linear model, but you don't throw away the nonlinear model. You bring your controller, close the loop around the nonlinear system, and test your system. Okay? Test your validity of your design. A lot of times it's good enough, but sometimes you may be pushing the system in a region where the linear model is no longer valid. Remember, you're doing it around the nominal trajectory. If you're away from that nominal trajectory, far away, it may not work. Okay? So, those are issues of control for a nonlinear system like manipulated robot. So control is another aspect of the issue. And sensing, we went through 3 lectures of sensing last week. I want you to actually review those slides and learn how you could do some quick calculation to estimate the value of a sensor, for example, in a potentiometer or a voltage divider, or you have other types of sensors. So you also need to know why do we want to sense anything. Okay. So sensing is the most fundamental thing that you can do, because if you cannot sense a variable, you can never have a chance or hope to control it. You see, you need to be able to control it. And in that sense, data is becoming such an important issue. Now, in terms of manipulated robot, let me see if we have any. For example, what is a redundant robot or under-actuated robot? Redundant robot is a robot which has more degrees of freedom than is necessary. Okay, almost all space robots. There is a big subject called space robotics, which actually I have a book edited by a couple of my former students at NASA, and those are all redundant robots, because in a space you need to actually have an arm-looking person or a robot which can do a heck of a lot more than a human arm can do. Okay. We can move in a situation where you're going to break your arm, you cannot do it. Okay? That's why a snake robot is a redundant robot. It has several degrees of freedom. The snake robot that we built in the lab by a student and his team, it's got 14 degrees of freedom. Okay? So, and that snake robot can go to places where no human can handle it. Okay? Under-actuated manipulated is the opposite. You have a task which requires 6 degrees of freedom, but you only have 4. So you're not going to be able to do it. Okay? Okay. We are not going to be concerned about walking robots because we haven't covered it. Jacobian is important. Transformation between joint velocity and Cartesian velocity. You need to read on that. And again, your appendices are important too. You can take a look at those appendices in the book. Okay? And in the dynamic portion, you remember that we used Newton, Euler, and Euler-Lagrange equations for creating a partial differential equation which shows the dynamic behavior of a manipulated robot, where the control variables are forces and torques, and the state variables are joint angle, joint velocity, even perhaps acceleration and so forth. So there is a nonlinear model which is so consistent. You can look at an nth order, n-dimensional or n-degree of freedom robot, look at the Euler-Lagrange equation, and if you reduce it all the way to single degree of freedom, guess where you are? You go to the dynamic model of inverted pendulum. Okay? It's that consistent. Okay? But it's very messy. You know, your nominal textbook has skipped all the messes and went to the toolbox. But I showed you all the messy thing about that in the book by Fu and et al. In the robotics book, which is about 20-year-old book, but it's still a very valid book. Came out of Purdue University. So learn basically the meaning of a lot of terms. Okay. Your question will be a small, short calculation and some definition and some reason why this thing works. Okay. So, any questions so far on this, or we'll probably leave the questions after. Make a note up to yourself if you have questions. When we get off the air, we will answer that, because the final exam for the North Carolina student will be different than yours. Okay, and they have different experiments, different projects. Okay, but they listen to all the lectures that we had here, including guest lecturers. Okay, the second phase of the course was mobile robotics. In mobile robotics, starting from chapter 4, you look at a dynamic model of a mobile robot, which is the third order nonlinear model, including sine and cosine of the variables, as well as the x and y coordinate of the center of gravity of the mobile robot. Now, before we started, as you recall, Bharat was talking about you going to experiment 3 and measure the odometry error. When you want to measure odometry error, make a rough estimate of the center of gravity of the Pioneer robot on the floor, and then go from there to the designated destination. That's your error in terms of centimeters or inches or what have you. Okay.
And approximately 20 to 23 centimeters from the beginning.
One way, when we grade your experiment number 3, one way to judge is to see what is the distance between different groups. Okay? So how good yours were, we can compare. So if you don't like the first error, keep repeating that and try to fine-tune your controller, play with some of the parameters of your control algorithm. If you have PD controller, look at the proportional and derivative gains. Do some investigation, do some trial and error thing. Hopefully you can keep improving on the odometry error. Okay. And do a video. I like to see the video.
Yeah, they should take a video.
We like to see a video of what you have done. In the past years, sometimes I actually know where the students are in the lab. I go there and I watch them. Okay. So I may have a virtual camera there watching you. Anyhow, so be familiar with kinematic of mobile robotics, which is much simpler problem than manipulated kinematics, even inverse kinematic. But the problem with kinematic of mobile robot is a problem called localization. So what is localization? What is dead reckoning? These are the things you need to understand. And learn the foundation of trying to correct odometry error through estimation theory, for example, Kalman filter. I don't expect you to do Kalman filter on the exam, but I expect you to know how it works, why it works, and what does it do for you. Okay? What does it do for you? You look at the disturbance in the sensor information, look at the noises in the dynamic of the robot, and you account for odometry errors in terms of white Gaussian noise, corresponding covariance matrices for them, and then you have some landmarks around the robot where you know exactly where they are, and that will give you data, information where the Kalman filter can optimize. By optimization, I mean reducing the odometry error. Okay. For the experiment number 3, I'm asking you to do hit and miss, but in real situation, for more advanced beyond this course, you could put an active Kalman filter on the robot itself and will correct itself. Okay? These are the kind of things that I expect my research students to do when they're doing masters and PhDs. Okay? To actually implement that.
Actually, we did a homework last year about extended Kalman filtering for the suborbit satellite.
Yeah, but I think this, did I not assign any extended Kalman filter this year? No? But you guys are getting it by very easy. Not only that, last year, the final exam had 2 parts. One on the toolbox, one in writing. Okay? And everybody had a laptop in front of them in the exam, and they finished the robotics toolbox part of the exam, and then they switched it to the other one. This year I was easy on you because we pushed through into cloud computing and so forth. I'm hoping that you also are taking cloud homework very seriously. It is a good chance for you to really put something tangible on your resume and in your toolbox of knowledge and things which you can go for a long way. Okay? So, the navigation, what is navigation? You got to know that. How can you combine navigation and localization together? Some localization approaches finds your location with some assumed error, like your experiment number 3. You know, and in advance you're going to have error because there's not enough smart software on the robot to correct the mistake, correct the odometry errors, like extended Kalman filter, for example. In your chapter 6 of localization, the author did a fairly good job and start with the simple way of looking at localization and gradually make it more complicated. And in the process, you can do, in the process of localization, you can actually build your own map and you go along. That's why it's called simultaneous localization and mapping. SLAM, okay? Which some of you are doing in your project. So SLAM is also something you need to understand what it is, okay? And be able to describe it in a meaning where, you know, the question that we are going to be hope to read from your exam is as though we don't know what SLAM is, you're going to teach us what SLAM is, okay? By a few sentences, okay? Occasionally you may also give an example, a small graph, say this is SLAM, okay? Now, visual SLAM, we haven't done much on it, so don't worry so much on that, but those of you who are going to be doing it for your future, that's a different ballgame. You're going to spend a heck of a lot of time in the lab, okay? And visual SLAM has to be necessarily on the cloud because image processing is a very time-consuming, computationally intensive process, okay? So, in terms of quadcopters, again, we didn't go into much detail of it, so at least you basically try to understand the basics of quadcopter. How many motors it has, in what direction those motors are rotating, and how does it maneuver it, how does it move, comparing the behavior of the rotors, those fundamental things about quadcopter, okay? Then we will come through your knowledge, your basic knowledge of some of the things that I brought outside of the book, and that is fuzzy logic. What is fuzzy set? What is fuzzy logic? What is fuzzy control? How do you use fuzzy system theory to control a system? I think I gave you a homework on a pendulum. And I assume it came out very good. And so, huh? So, anyhow, the graduate students in the class, I expect them to have much better grade than undergraduate because some of the things are, honestly, is beyond the undergraduate curriculum, okay? But you are suffering along with it, okay? But there is no gain without the pain. Remember that. No gain without the pain. If you don't sweat, you're not going to succeed. Believe me, okay? So, in In other words, if you want to take it easy, you really shouldn't be an engineering student. Okay? And in terms of neural network, we didn't do a whole lot. In genetic algorithm, we didn't do much, you know. But at least on the fuzzy side, you need to know all these basics. What is membership function? How do you compose the rule? Okay? For example, imagine that you're going to balance a baseball bat on the palm of your hand, and it's going to fall down. So how you balance it? That knowledge that you have, even maybe a 12-year-old kid can do that. That knowledge can be changed into fuzzy if-then rule. Okay. All right. Now we come to the gas lectures. Dr. Benavides covered Python, you remember, and he covered ROS. You need to know the most basic attributes of ROS. Okay. Those are the kind of questions that if you go to an interview for a job and they're interested in hiring you, like my student Ahmed, who took this course 2 years ago, is now working at Southwest Research. And he's conducting a ROS workshop for ACE students. And the kind of questions that you, on this exam, you need to answer me is the kind of question that you may face it in an interview. You see what I mean? That you could actually be able to intelligently and very comfortably answer a question in the interview. Okay. I think basic aspects of Python is important. That's why you review your homework, because we had all those homework on Python, homework on ROS, and so forth. And then on the basic paradigm of cloud, OpenStack, cloud infrastructure. What is Hadoop? What is MapReduce? You know, what is software for as a service? Infrastructure as a service, etc. These are the, again, fundamental things that you would be taking with you way after the class, hopefully in your next job or first job or what have you. So, at this point, let me see why am I missing anything. For the exam, you don't need any cheat sheet. Just be able to actually, unfortunately, you have to read it enough to memorize it a little bit. Okay. If I give you a problem to work out by hand, like finding inverse kinematic of a tooling robot, you know, I may give you some equations for that. Okay, but what is the meaning of inverse kinematic? I'm not going to help you. Okay. And actually, I'm not even here to help you. Next week, Bharat will be here. But he's more helpful than I am. But don't ask any clues. Okay. The student come and ask for a clue to solve the problem. Okay. Okay. Any questions? You all already in the A category for the grade? Don't be bashful. The one next to you doesn't know it either. So ask the question, the whole class will benefit. Okay? Question number 1. If you don't ask question, I'm going to ask Bharat to ask question. Then you will benefit what he's talking about.
Are you going to ask us quaternions?
Pardon me?
Quaternions on the test?
The question is whether quaternions on the exam, no. Yes.
Will there be like MATLAB on the test at all, like written MATLAB?
Is there any math lab on the quiz? No. On the exam. No, I can't do that without you having access to the toolbar. Okay. Another aspect that I am hoping that, I'm getting very anxious about the project day, May 9th, okay? And I hope you have very good results. I need a report looking like a conference double column paper. And if I see that your result was good quality, we can turn it into a technical paper. Okay. And we also need a slide presentation. Keep the slides down to less than 9 in 1 digit. 10 or more, not so much. Okay. And as I said before, if you are 3 of you in the group, at the beginning tell us who did what, and just use one of yourself to present the whole thing. I trust you that you have said the right thing. It's an honor system. Okay? And this way we can have faster turnaround. So, because so many people are going to be there, and the other class also will be there. Okay. And Parag will make a sign-up sheet from, let's say, 1 o'clock on Monday the 9th, all the way as long as we have to go. Up to sunset if we have to go.
And everybody has to show up, right, Professor?
They have to show when they are scheduled to show up. But if they are really thirsty for knowledge, they come there and they spend a few hours. Then learn a lot more things.
I mean all the group members.
Yeah, all the group members have to show up in their own slot. See how many groups we have, and whether we can afford to have 20-minute slots or 15-minute slots.
15 will be better, Professor. We have more than 12 groups.
12 group in robotics,
Yes, Professor. Let me check because
and we got the 6 group in big data analytic course. They're also coming on that day.
but two students actually is already here.
I know, but they have to have different projects.
Yes.
I'm not giving them
So
2 grades for one project. I'm not going to do that.
No, actually we have 4 students. Oh, and twins. Yes.
Especially if they're graduate students. Okay.
Let me check, Professor.
So in any case, projects is very, very important part, and May 9th would be the big day for this course. And again, hopefully you get it to work in real time and immediately take a video and bring the video to the presentation. I don't expect anybody to do any demo, but if you do have demo and you like to do demo, let Berat know and we'll try to make some extra time for you. The next question. Yes.
For the project report, since we have already made a back paper of the same project, do I have to submit a separate report, or can I submit the back paper itself as a report?
Get rid of your co-authors and revise the co-authors who are not supposed to be there, like me. Okay. And then go over it again, because your work we do with Nico and Nicholas.
Yeah.
And Abhijit is also in that group.
No, sir.
Just the 3 of you. It's continually work in progress. So bring it up to the latest thing that you have done. Okay. And speaking of your project, know, you have a UAV and 3 ground vehicles. Have you tried cloud yet?
Yeah, we did.
We have, yeah.
You have done it?
Well, we did it, but it's, with that router we're using right now, it's kind of, well, actually, no, we need to test it on the router, but through a Wi-Fi dongle, which we're using already, the lag was just terrible. And it looked like, if someone walked through the frame, it looked like they were walking through in slow motion, real choppy.
Okay, the question is, you know, can they do image-based identification of ground vehicles on the cloud? You need to assess in that project, which I call it the Humboldt. Okay, it's really a mini project by itself.
That can be done.
Huh?
That can be done. Image-based identification can be done.
Now, identification doing cloud, I am curious about network delays. Because in real time, cloud may not be a good idea. Because by the time the cloud, you can get it from the cloud, especially if it is much larger cloud. This, of course, is our own private cloud, which may be better than, let's say, if you have UTSS, large cloud infrastructure to be used, let alone, for example, public clouds. So there was an argument even yesterday in North Carolina with some of my fellow professors there, whether cloud-based robotics for real time is going to be fast enough. So if something goes wrong, don't throw it away. Bring it up and find out why. See, that's important. And you can actually put that in your papers and even your thesis. See, so it may be that cloud be more useful when you move the robots to outdoor, put GPS in place of vision identification, and then cloud may be better that way. So this particular project is going to go quite a long way, all the way probably to the end of December. Okay. All right. Any other question besides what's on the exam?